Last class, I explained how to avoid collisions by using chaining. In this case, we maintain a linked list to store all the keys to be hashed to a slot like this. If 3 keys are hashed to a same slot, then all 3 keys are maintained by a linked list. Today, I'll explain a different approach, which is open addressing. Open addressing is another method to resolve the collision. We don't use linked lists because all elements are stored in the hash table itself. So it avoids pointers altogether. And the extra memory provides the hash table with a larger number of slots for the same amount of memory. Do you understand this? Okay, let me explain this later again. There are 3 famous open addressing methods. And the simple list one is this, linear probing. Okay, I will explain the linear probing by this example. We have a hash table with 13 slots. So M is 13. And we use the division method to store the key. And in this example, keys are inserted in this order. And let's see. First, key 5 is stored. Then 5 modulo 13 is 5, so it is stored here. And then 14. What is the hash value of 14? Park Jong-hun. What is the hash value of 14 in this case? 1, yes. It is stored here. And then Park Geun-bae. 29. 3. Yes, 3. Kim Bum-jin. 25. 12. Yes. Jang Hyung-min. 17. 4. Yes, 4. Bae Min-hee. 21. 8, right. 신지수. 박준규. 18 is stored, should be stored in the 5th slot. But this slot is not empty. It is occupied by a key 5. Then what should we do? Very simple. Just check the next slot, and if it is empty, we store it there. That is linear probing. And then 최소리. She isn't. 김종빈. And then next, 32. 6. But it is occupied. So then we check the next slot and put it there. 신경식, 어미송. Okay, the next key is 20. What is the slot number? 9? 9? Oh, okay. It's anyway, its hash value is 7. And then check the next slot. It isn't empty, so check next slot, and it's stored at 9. And then the next key is 9. So we store it in the 10th slot. And 15. Okay, and 27. It should move a long way, and then it is stored in the 11th slot. This is linear probing. Okay, then I will explain open addressing formally. Insertion is like this. It examines the hash table until it finds an empty slot. Examining the hash table is called probing. And the sequence of positions probed depends on the key being inserted. And this is the probe sequence for every key k is written like this. This is the hash value of key k for the first probing, and second probing, and third probing. In the case of linear probing, it's just +1. But in general, it can be any permutation of slots. Okay? Any permutation is possible. Okay, this is the algorithm for hash insert. A general pseudocode. It takes as input a hash table and a key. So inserting key k into a hash table T. Okay, look at this pseudocode and try to understand the meaning for a couple of minutes. Yes, perfect. Yes, that is. So we check each slot if it is empty or not. And if it is empty, we can safely insert a new key into the slot. But if it isn't empty or occupied, then we have to check or probe the next slot. But if we probed all the slots and there was no empty slot, then it means the hash table is full. Okay. Okay, this is a pseudocode for searching in a hash table. Look at this pseudocode for a minute and try to understand its meaning. Why Tj is nil is the exit condition. I can understand that. Okay, I equals m means we approved every slot, and there isn't k in the hash table. Okay, and there is another exit condition of this loop. T of j is nil. Why this condition is added? Empty. That's why I asked you the question in the search. So these two things are related. So we cannot remove the key physically. If we remove them, if we remove it, then the search function doesn't work properly. So instead, we mark the slot by the special value deleted. It can be any integer, such as -1, -2. That is some invalid value. Then the problem is, this. Okay, I'll ask you. Then the correctness, there is no correctness problem. And then I'll ask you a question. Then new key is added, deleted. And we have to change the search procedure or the insertion procedure a little. How much do we have to change these procedures? First, let's see insertion. 한상현. Okay. What should be modified to accept the deleted value? Deleted, I mean changing the insertion. 강인구. Yes. So deleted means it's empty. So when we insert a key, we check if the slot is nil or deleted. Then we can safely insert the key into the slot. Okay, then that is insertion. How about search? 박성현. In the 8th line, what? Nil or M or deleted? Sorry? Nil or deleted? Really? 윤호상. And this problem has appeared several times in your midterm. And so what should be changed in this hash search? Then the answer is nothing. So if you write anything, you're wrong. But at least you should say nothing or X. I mean, you should write nothing or X. I'm not saying you don't write anything. And I said this several times. Last year, I said this, but some students try to change the pseudocode, and later they say, oh, I laughed when I said, but I didn't know it was this problem. Okay, but the running time increases, especially search time increases, because if we don't use this, the search time depends on the number of keys which have the same hash values. But in this case, because of the deleted keys, even though there is only one key is stored, if 10 keys were added and 9 keys were deleted, then the running time is proportional to 10 keys. So, for this reason, open addressing is used for non-deletable keys. And if keys must be deleted, chaining is preferred. Okay, now I will explain 3 common techniques for open addressing. And I explained linear probing. And then I'll explain quadratic and double hashing. Formally, linear probing is defined like this. Given an ordinary hash function h prime, and it is called an auxiliary hash function. And linear probing is like this. H of ki equals h prime k plus I. So this means probing the next slot. And we did this. But linear probing has a severe problem, this. Look at this. And next, so 32 is stored here, and 20 is stored here. 9 is stored here. So what do you think is the main problem of linear probing? But we don't care the orders of key insertions. So look at the collision. 조정환. Look at this. So, how many collisions are there? If we create this using the chaining, how many collisions are there? Okay, there is one collision here. This is not a collision if we use the chaining, because 18 was stored here. Is this a real collision? No. No. So, even though we have only one collision, collisions are infectious. So, if there is a collision in a slot, its adjacent slots suffer collisions. Okay? That is the problem of linear probing. And it is called a primary clustering. Long runs of occupied slots build up, increasing the average running time. So, quadratic probing tries to solve this problem. And its function is like this. H of ki equals h prime k plus some quadratic function. So instead of checking the next slot, we check it in a different way. Let's see. So this is a simple quadratic function, k plus I plus 3i squared. So this is the same key sequence. So when I is 0, it is the same as linear probing. So it means if there is no collision, then it is stored using the original hash function. That is 5, 14, 29, 25, 17, 21. Okay, this is the first collision, 18. And then, where should it be stored? Let's use this hash function. In this case, I is 1. So k plus 4. So we check 1, 2, 3, 4, which is 9, and then it is stored here. So instead of checking the next slot, we jump to next slot. Okay, then as I told you, this was the only collision. And all the other collisions are pseudo collisions. Then 32 is stored without collision, and 20 is stored without collision. And then 9, this is a collision. And then we check 1, 2, 3, 4. So it is stored here. And then let's see. It is 15 and 27. Check 1, 2, 3, 4. And then it is not empty. So in this case, I is 2. Calculate. So look at this hash table. So only 2 slots are empty. So the probability of finding an empty slot is very low. So this is inevitable. Okay. So quadratic probing resolves the primary clustering problem. It's better, but it still has this problem called the secondary clustering. That is, if two keys are hashed to the same slot, then their probing sequences are all the same. Do you understand? So, if another key, assume that two keys are hashed to this slot, and their probing sequences are the same. So, in some cases, a lot of keys are hashed to a slot. Then you will suffer a long chain of probing sequence. It's called a secondary clustering. Then how can we solve this? It's simple. We use two hash functions, double hashing. This is the initial hash function, and this is the second hash function. So this second hash function differs from the initial hash function. Let's see. In this example, the initial hash function is like this, and the second hash function is like this, 1 plus k modulo 11. And let's see the difference. So, even though two keys have the same value of their first hash functions, their second hash function values are different. So, the probing sequences are different. That is the idea of double hashing. Let's see. First, okay, collision. Then let's see where it should be stored. 27 modulo 11 is what? It is 6 plus 1 is 7. So we check every 7th. Slots. 1, 2, 3, 4, 5, 6, 7. It's 8. Sorry, 7th. Okay. Strange. 27 modulo 11. 20 to 5 plus 26. Yes, it's 6. 7 and 0, 6, 12, 5, 11. So as I told you, if only a small number of slots are empty, it is very difficult to find an empty slot, even though you are using a very, very good hash functions. This is impossible by the probability theory. Good hash function is like this. If we have enough space, then it finds an empty slot very fast. Okay, this is double hashing. And then there are some restrictions. The value h sub 2 of k, that is the step size, must be relatively prime to the hash table. Why? Relatively prime to the hash table size. If it is not relatively prime to the hash table size, such as assume that we have 4 slots in the hash table and the step size is 2. Then assume that there is a collision here and then check here. And if it is not empty, we check here. So we only check a small portion of the hash table. So they should be relatively prime. Relatively prime in Korean is 서로소. Okay? And a simple way to ensure this condition is to let m be a power of 2. So table size is a power of 2. And then every odd number is relatively prime to the table size. Another way is to let m be a prime. And to design h sub 2 so that it always returns a positive integer less than m. Because m is a prime, any integer less than m is relatively prime to m. Okay, so the range of the midterm exam is up to here, up to hashing. And in the next class, we will talk about self-study questions and hard review questions. Because we have some time today, about 20 minutes, let's check out some review questions. Do you have review questions? Let's see the questions in the review from review 1 to review 8. I don't think review 1 is, I don't think there is no difficult. I think there is no difficult in review 1. So, okay? No questions on review 1. And review 2. The only difficult question in review 2 is number 4. But I explained the Arnold's rule. So, done. So there are 4 arguments. An array A, and P and R are indexes of the array. So we consider a subarray of A, starting from P and ending at R. And in the subarray, we are going to find the ith smallest value in the array. Okay, that is the sub-question A. And then the sub-question B is, what is the worst case running time? Anna, what do you think? N squared. Why? Can you explain? 최용준. Sorry, not 최용준. 박종훈. So, what do you think? Okay, so before we talk about running times, let's read the pseudocode. Can you explain the main idea of this pseudocode? 박종훈? How to find the smallest element in this pseudocode? 박근배, 김범진. Yeah? Yes, the partition in the quicksort. Can you elaborate your explanation? Okay, let me explain it using an example. Okay, let's assume that there are 6 elements in this array, and select. So assume that it is the whole procedure is finding the third element in this array. Okay? Then we first run partition here. Okay. Assume that it is a randomized partition. So there are 2 cases. Let's change these 2 values. It's not 7. 7 is here, and 2 is here, and 3 is here. Okay? This becomes the pivot, and if we use the partition, smaller elements and larger elements, and pivot is here. I don't guarantee the orders here. So partitioning doesn't guarantee the orders in the subpartitions. Okay, then let's write it like this. And now we are going to find the third smallest element. Then look at this. There are 3 smaller elements and 2 larger elements, and the position of the pivot is the 4th. So we ignore the larger element from now on. We dive into the smaller partition. That's the main idea of this selection procedure. And what if it was 5? The 5th element, the 5th smallest element. We know that it is in the larger partition. Okay? Then we recursively use select on this larger partition, but in this case, we have to change the order. 4 minus 4, which is 1. So we have to select the first smallest element in this larger partition. Catch this? Did you catch this? So it is written in the pseudocode. Okay, then what is the worst case running time of this algorithm? As Anna told, it's n squared. Because if it is very unlucky, then the pivot is 7, 5, 3 in this way. So if the partitioning is bad, its running time is n squared. And what is the best case running time? What is the best case running time? Set theta of n. Why? Yes. We can find if the smallest element is the pivot, we can find the element using only one partition. So it takes theta of n time, and the best case running time is theta of n. And what is the average case? It is also theta of n, because n over 2, n over 4, if we add all the values, they are theta of n. Okay. Okay, then wrap up this class now and see you next Wednesday. If you have any questions, but you can't speak in English, ask me after this class in Korean. In your case, use English after this class. Okay, see you.